And after class, I'll pass back the last two quizzes that I graded. But yeah, those grades are up. You should see those on Canvas. And then I also posted the solutions and the rubric, which you can find on our class Google Drive under quiz something. Yeah, under quiz solutions and rubrics, I posted the keys for quiz 3 and for quiz 4. All right, howdy. Good afternoon. Thank you all for being here. Hope everyone is doing well. Happy Wednesday. Today is our last class before exam one. What we see in this lecture will conclude the material that will be covered on exam one. So you could, and this will also conclude the questions that you have on problem set 3. Once we finish today, you'll be able to have seen everything that you would need to see to be able to finish up problem set 3. Um, so yeah, today we're gonna kind of pick up where we left off last time. Um, we're gonna develop the multi-group diffusion equation, and then we're gonna kind of unpack the equation to get more comfortable with how to use it and how to do applications with that equation. So just kind of like quickly refreshing what we talked about last time. Um, we we went from one group diffusion to a two group diffusion model where we considered a fast group and a thermal group. And we kind of did the exact same thing that we did with one group diffusion in that we considered all the gains and loss mechanisms that the neutrons could have, but then we considered them from within each group. And so the main thing that was different was that we had those scattering reactions that could cause neutrons to be exchanged from one group to another when scattering reactions happened. So this was kind of like the picture that we used to develop those equations. And those equations basically just said rate of change of my group population equals all of the rates of gains of that population minus all the rates of losses of that population. And when we did that, we got these two equations where you basically have a diffusion equation for each group of neutrons. And there were some interesting things about these equations, like the fact that because of the nature of fission being a reaction where neutrons that are fast, so the Phi1 neutrons, and that are thermal, the Phi2 neutrons, both of those neutrons can cause fissions. So it's both fast and thermal neutrons cause fissions, and then those fission neutrons that come out of the fission reaction, they can either be born fast, which is the chi1, it's like the fraction of those total neutrons that are born in group 1, and then there was a chi2, which was the fraction of those total neutrons that are born in group 2. So that's an example of the coupling between energy groups. The fission reaction is a way that our energy groups get coupled. And then there was also coupling because of our scattering reactions, that neutrons can be scattered out of the current group and into the other group. So like if we're looking at the flux one equation, the fast flux equation, neutrons can get scattered from the high energy group into this group, and neutrons can also get scattered, and that's why there's a plus sign here, because this is a gain term for group one. And then there was a minus sign in front of this term, because these are neutrons from group one that are getting scattered out of that group one into group two. And then we see opposite terms in group two, because anything that scatters out of group one, it's lost from group one, but then it's gained in group two. So these terms are equal and opposite for that reason. So scattering is the other way that our energy groups are coupled. Um, and this was kind of we use the framework of this equation to then develop or really kind of hand wave what the energy dependent diffusion equation would look like. So that was where instead of having subscripts to say these are the neutrons that belong in a certain group, we use energy dependent quantities. So like in here, the flux is the energy dependent scalar flux, which is kind of like the regular flux, but it has extra, instead of it just being path length rate per unit volume per unit time, which would be the units of the regular flux, it also has per unit energy units. The energy dependent scalar flux is also effectively a density in energy. Um, and so in this equation, because it's energy dependent, every single one of these terms is is telling us about a reaction rate density that is also per unit energy. So like in terms of the physical interpretations of these things, they kind of have the same meaning that they had in the one group diffusion equation, but now everything is energy dependent. So they also tell us about every quantity is per unit energy. Um, and so what we're going to do today is we're going to develop a multi-group diffusion equation that is going to allow us to deal with the fact that this equation is not analytically solvable. So we're going to kind of get around that with this multi-group diffusion approach. So if it's a real reactor, that energy dependent diffusion equation isn't really like analytically solvable. So what we would do instead is that instead of making the energy be a continuous variable, we break our energy axis up into a bunch of little groups. And then we can take that energy dependent diffusion equation, we can integrate it over the energy range of that group, and then the result of that equation will tell us something about the flux of neutrons in that little group, and it'll also tell us about the average properties of our system within that group. So if this is like our energy axis, the first thing that we are going to do is we're going to divide the entire energy range into big G number of groups. So each of these like little intervals corresponds to a group, and then each group has a minimum and maximum range. So like this is the direction of increasing energy. So E0, that's going to be like our maximum neutron energy. That's going to be like around 10 MeV is a pretty good cutoff point for like the maximum energy. And then all the way over here at E sub big G, that's going to be our minimum energy, which is going to be about 0. And so if I look at any particular group, like if I look at if I look at just group 1, then the range of group 1 goes from the minimum value would be E1 and the maximum value would be E0. And if I look at a generic group G, then the minimum value of this energy is E sub G, and then the maximum is E sub G minus 1. So any energy range for the group little g is going to say, it's going to look like my energy is in between E sub G and E sub G minus 1. And that holds for any group that I look at. Like if I look at group 2, that means that little g is 2, and that means that the left bound is E sub G, which would be E sub 2, and then the right bound is E sub 1. G minus 1 would give me 1 if it's group 2. And so this is in practice how we can discretize and break up our energy range into a bunch of little groups. You can use like an arbitrary number of groups. Like maybe you have a 3-group model, so big G is just 3, and then you have 3 little intervals within that range. You could do 100 groups, and then you would have a bunch of little, that would mean big G is 100, and then you have a bunch of little intervals that you have to consider. And again, we use backwards indexing on the subscripts here, and that's because of the fact that neutrons are born fast and then they thermalize and they slow down as they go through their life in the reactor. So this is our energy discretization, and what we're going to do is we're going to take that energy dependent diffusion equation and we're going to integrate it over the group G width. So this is just taking that diffusion equation and then integrating it. Each term is being integrated from over the group width range. So if we're looking at group G, the little g energy group, then we're integrating each term from E sub G to E sub G minus 1. And it's going to be helpful for us to define the group G flux. And so effectively what we're doing is we're taking a energy dependent scalar flux, and then we're trying to take the energy dependent scalar flux and turn it into like a regular scalar flux. So if I have the energy dependent scalar flux, what do I have to do to that quantity to convert it into just a total scalar flux? Perfect, right? If it's energy dependent flux and we integrate that over energy, that is by definition going to give us the regular scalar flux. So to get the group G scalar flux, I'm going to integrate my energy dependent scalar flux. I'm taking that energy dependent scalar flux, I'm integrating it with respect to energy, and I'm integrating it over that little range for that group. So I'm integrating it from E sub G to E sub G minus 1. If I were to have integrated from 0 to infinity, that would give me the total scalar flux, which represents the path length rate per unit volume per unit time of all neutrons in my reactor. Here, because I'm only integrating over this tiny little energy range, phi sub g is basically just telling me about the scalar flux of neutrons that have energies within group G. So it's saying that it's the path length rate density or path length rate per unit volume of neutrons with energies that are within EG less than E less than EG minus 1. So that's basically like my flux of group G neutrons is basically the way to think about it. And so if we have this definition for the group flux, then we can start kind of interpreting each term individually, and we can try to simplify this equation to derive the multigroup diffusion equation. And so that's what we're going to do moving forward. This is just kind of interpreting what each of those quantities represents. So before, when I had the energy dependent diffusion equation, every quantity in that equation was a rate density, also per unit energy. And I've effectively taken that energy dependent rate density and I've integrated out the energy, which means that the energy units that were in the bottom now get canceled out. So now each of these terms just represents a rate density. Each of these terms has units of neutrons per unit volume and per unit time. Because before it was neutrons per unit volume, per unit time, and per unit energy, but then I'm integrating out the energy information. So in this sense, each of these terms kind of has a similar meaning to what the quantities had in one group diffusion equation. But now, because I've integrated over this little range, it represents production or losses for the neutrons in group little g. So this would, for example, be the number of neutrons per unit volume per unit time that are leaking out of my reactor from and that are within that little group G. These would be the total number of neutrons per unit time per unit volume that interact within that group G. These would be the total number of neutrons that's per unit volume per unit time that scatter from some other energy into our current group. And then these would be the number of neutrons per unit time per unit energy that are born from fission into the current group little g. So these are all just production and loss terms, but just for the neutrons in group little g. So the way that we're going to move forward is we're going to go term by term and we're going to think about how we could simplify those quantities. And part of the way that we're going to simplify them is we're going to make clever use of an average value of a function. So this thing right here, this is by definition the average value of a function. You should have seen this. I think it's covered in Cal 2. This is how you could take the average of a function. If f is the function that I'm trying to take the average of, what I do is I integrate that function over the whole domain. 0 to infinity is just saying over the entire domain of the function. And I take that function multiplied by some weight function, and I integrate that, and then I divide by the integral of the weight function. And it kind of depends on the context of the problem, what that weight function would be. Like when we did the definition of mean free path for neutrons, then that weight function was the probability density function for neutrons having an interaction in the material. If you wanted to develop a mean lifetime equation, that weight function is going to be like a probability per unit time that decay happens. So it kind of depends on the context of what that weight function is. Um, and so, but if we keep this definition in mind, then the first thing we're going to look at is that total interaction term. So this guy right here was that total interaction term. And notice right now, all I've kind of just said is that that thing equals itself, right? These two quantities are the exact same. And don't write what I write next, but I just want to illustrate that if these two things are equal, then I could take this quantity and I could like divide and multiply by the same thing on top and bottom, and it doesn't change what that expression is, right? These are exactly equivalent because all I've effectively done is multiplied by one in a clever way. And it could be something more complicated than 5 too. Like I could multiply both sides by e to the negative x. And if I multiply top and bottom by that same thing, then I'm not fundamentally changing what that quantity represents. So the thing that you would want to write is what if we multiply top and bottom by this integral, by the integral of e to g, e sub g minus 1 of my energy dependent flux. I'm going to divide by the integral of my energy dependent flux from Eg to Eg minus 1, and I'm going to multiply by that same thing. Notice I haven't changed the quantity because I've just multiplied top and bottom by the same thing. So hopefully we see that that's okay. And then we can kind of look at this with two terms, but we're going to look at this term by itself, and then we're going to look at this other term by itself. So notice the way that this is looking now inside the blue brackets, that if I compare the definition of an average to this quantity right here, doesn't this kind of look like an average? Doesn't this kind of look like a weighted average of my total cross-section weighted to the energy-dependent flux as my weight function? So if we can recognize that this looks like an average, that's kind of what we need to move forward. And this is what I mean by making clever use of an average. That this quantity right here technically is the group averaged total cross-section. So in the brackets, that by definition is sigma total for that particular group G. That's just by definition of an average. That's my group averaged total cross-section. So hopefully that's okay. And then what it is being multiplied by, I'm integrating my energy dependent flux over that little group width. So by definition, what does this little integral have to be? Yeah, perfect. That's just my group G flux. So I'm going to say that's phi G and it depends on R. So notice we've taken this complicated looking integral and we've just rewritten it as a product of my total group average cross section times the flux for that group. And yeah, and so what that total group cross section is, it's just my total scattering, sorry, my total cross section for neutrons that have energies that are within that group G. And by definition, if I were to think of this thing as like the left side of my equation and this thing as the right side of my equation, then I could divide both sides by that group flux to get the sigma total by itself. And that's what this definition is right here. I'm just taking the group flux, dividing it on both sides to write the total cross section in that form. And that also looks kind of like the this is also basically a definition of an average. I'm integrating that total flux over a range with the phi, with the energy dependent flux as the weight function. And then in the bottom, I'm integrating over that weight function. But when by definition, the integral of that energy dependent flux over that group width just gives me the flux for that group. So that's what our total interaction rate density term would look like. And we're going to kind of play a similar game with the other terms in our equation. So the next equation, the next term in our equation that I want to look at would be our fission production rate density term, which was this guy. And the first thing I want to look at is just this little energy integral over the integral of my fission spectrum. Um, Remember that by definition, the fission spectrum is a probability density function. And if I take a probability density function, if I were to take chi of e and integrate it from 0 to infinity, what would that give me? What would that have to be equal to? It would be equal to 1, right? Because it's a probability density function integrated over the whole domain by definition is 1. But instead, I'm integrating from e sub g to e sub g minus 1. I'm taking that fission spectrum and I'm integrating just over that little energy range. So this is not going to be equal to 1. This is going to be equal to the fraction of my neutrons that are born into that particular range. So I'm going to say that this is equal to chi sub g, which basically is just the fraction of my neutrons that are born into group G. And if I have a bunch of different groups, then I'm going to have a chi sub g for all of those groups. But either way, if I were to add up the chi g's for every single group, then that total would give me 1. So by definition, we normalize this such that if I were to sum up from g equals 1 all the way up to big G of all of my chi g's, then that by definition would give me 1. And we kind of saw something similar when we did the two group model, where we just had two groups. So we just had a chi1 and a chi2. And we said that by definition, those two fractions have to add up to give me 1. This is just writing that same thing, but in a more general way to say that we could have any number of big G groups, and all of those little group fractions have to add up to give me 1. And so if I recognize this definition, then if I'm just looking at that quantity, that fission production term, that's what this little integral is. This is just chi g. So this looks like chi g over k. And then I've got this other integral over all energies. And so for this integral, the way that I'm going to tackle it is instead of integrating from 0 to infinity, I'm going to do a sum. And really, when we're integrating this, we're integrating over all other energies. That's what the E prime is. It's all other energies that I start with that feed into the group of interest, which is big E. So here, instead of having an integral, I'm going to have a sum. And basically what this term is going to look like is a sum over, I'm going to call it H. H equals 1 to big G, where this H is representing all of the other groups in my system. And then what I would also do is make clever definition of an average by multiplying and dividing by the same thing, such that what is in this sum is going to be a nu F times a sigma F, which is a function of position. And this is going to be a nu F sigma F for this group H times the flux of neutrons that belong to group H. So if I rewrite the integral as a sum over all other groups little h, and then I use clever definitions of an average, then I can rewrite this big complicated integral as a sum of effectively my group fission production terms. And I just, yeah, and so I'm basically taking the fission production term from every single group, adding those all together. If what's in the brackets here is basically my total production rate density. It's the neutrons per unit volume per unit time from every single energy group. And then when I multiply that by chi g, that says, okay, this is my total. And then if I hit that with chi g, it gives me the fraction of that total that's just born into the group little g. And so by definition, this is what this is kind of a thing where usually when you see nu F and sigma F, you see them together for production rate density terms. And they both will depend on the same thing. Like Nu F and sigma F will be like for your fuel or for your for some material in your reactor. So usually those two things are together. So I'm just kind of lumping them together as one term. And what this effectively represents is the average value of the little Nu F sigma F with a subscript H. That's the average value of that Nu F sigma F integrated or averaged over the energy range for group H. Um, so we have to keep track of two indexes because group little g is the group that we're keeping track of. And we're saying we can have contributions into this little group from all other groups, little h. So this right here is what our fission production term is going to look like in the multi-group diffusion model. We're going to do something very similar with that scattering term, because that scattering term also involved neutrons of some other energy E prime that were scattering into the current energy E that we were keeping track of. So what I'm going to do is I'm also going to write this an integral from 0 to infinity. I'm going to rewrite that as a sum going from h equals 1 to big G. And then I'm summing up the integrals of all of the little pieces. So like if you're integrating a function from 0 to infinity, that's the same. It's just the area under that curve. So I'm free to define that integral and then say, well, what if I took that function and I broke it up into a bunch of little pieces, took the integrals of all of those little pieces? By definition, the areas are still the same. That's kind of what I'm doing here, rewriting the integral from 0 to infinity as a sum of little integrals over their individual particular ranges. And then I make clever definition of an average by multiplying top and bottom of this expression by this integral, integrating that energy dependent flux, but just over the H group width. So from E sub H to E sub H minus 1. And then this quantity right here, what this is basically representing is the group average differential scattering cross section. So by definition, that quantity in the big brackets, that's my sigma S to go from group H into group G. And it can depend on the position in the reactor because different materials in my reactor would have different cross sections. So that fundamentally, that's what this term represents. It's a scattering cross section that gives me that relates to the cross section to have a scattering reaction that kicks me from some other group H into the group G that I am keeping track of. And then by definition, this thing that it's next to, the integral of my energy dependent flux over that little energy range, by definition, that is my flux of neutrons that belong to group H. So that is being multiplied by phi sub H. And this, oh, and I apologize. Sorry, this sum is not in the brackets. So I technically have two sums here. What's in these brackets is my group average sigma cross section. And then what I have to do, let's see, one sec. I need to make some room here. Can I do this? Oh, it won't let me take the whole thing. Shit. Um, okay, real quick. I'm gonna just delete this. Sorry. It's just those integral quantities that make up my weighted average, and then that sum is up front. So kind of like what we just saw with that fission term, that this thing right here is my weighted average. So I've got a sigma S to go from group H into group G. The integral on the right, that by definition is my group H scalar flux. So that's my phi sub H. And then I'm still having to sum over all of the other group, um, summing over all my other groups. So bear with me that I have a sum inside of a sum, but this is going to go from h equals 1 to big G. And really, it's not a sum in a sum. It's just that we use the term big sigma for a sum and for a macroscopic cross section. So this is saying I'm summing up these quantities. If I look at just what's inside here, this would basically represent the scattering rate density of neutrons that scatter from group H into group G. And I might have a bunch of different groups, and all of those groups, little h, can possibly scatter into group little g. So that's why I'm summing up over all h's, because once I have the sum here, I'm accounting for all of the other groups that scatter into my little group of interest. And so, yeah, by definition, this that scattering, the group differential scattering cross section is this integral right here, which is what I had in the brackets up there. Sorry about that little typo, but hopefully that makes sense. And so yeah, this right here is what my scattering rate density term is going to look like. And the last term that we have is the net leakage term. So the net leakage term was this guy right here. Um, the the divergence operator only acts on spatial variables. Like it's telling me to take derivatives with respect to like x or y or z or r. So I'm free to pull that divergence operator outside of my integrals. So that's what I'm doing first. And then again, I'm making clever use of an average, but instead of multiplying top and bottom by the integral of my flux over the group width, I'm multiplying top and bottom by the gradient of the flux. So this quantity in the brackets is like a weighted average of my group diffusion of my diffusion coefficient, but it's weighted to the gradient of the flux instead of weighted to the regular flux. So this, I'm going to have that divergence. This term, by definition, is the group G diffusion coefficient. And then by definition, this quantity right here, if I integrate my gradient of my energy dependent scalar flux over this little energy group, the gradient operator can also come outside of the integral because it doesn't act on energy variables, it just acts on spatial variables. So like if I pull that gradient out, then I've basically just got my phi for group G, but then because that gradient operator is there, that is effectively multiplying by the gradient of the flux of group G neutrons. So, and yeah, so by definition, that's what the group average diffusion coefficient is. And the group average, it's just the same as that diffusion coefficient from before, except now it's just corresponding to neutrons, diffusion coefficient for neutrons that belong into group G. And like hopefully that kind of makes sense in that if we remember our cross-section plots, that those cross-sections vary wildly with energy. And that means that the diffusion coefficient is based on my cross-sections. In fact, what we said before is that in general, the diffusion coefficient, we said that we could approximate it as 1 over 3 sigma total. But what we're going to do here is we're going to kind of modify that original definition, and we're going to say, in reality, the diffusion coefficient is better approximated as 1 over 3 times sigma transport. Um, and so the transport cross-section is kind of like a quantity that we take from the results of neutron transport theory to make diffusion more accurate, especially like at the boundaries. And so, yeah, But this is just what I was trying to say is that the diffusion coefficient is based on my cross sections. My cross sections vary with energy, and they can vary wildly with energy. So it makes sense to like average that diffusion coefficient over those little groups so that I can do calculations for that particular group just based on an average cross section and not use like some large yeah, it makes my calculations more accurate if I do it like this. And so what we're showing here is just basically saying that sometimes if we're trying to do a problem, we might not know in advance what the gradient of the flux is. So we can also redefine that group G diffusion coefficient, and instead of making it be based on a weighted average of the flux, we're just gonna, or sorry, what we did here was we made it a group we were energy averaging the diffusion coefficient weighted to the gradient of the flux. Here we're saying, well, if we can weight it to the gradient of the flux, it's not that much of a stretch to say we can just weight it to the flux itself. So this is just saying we can also define it by a weighted average over the energy spectrum instead of the gradient of the energy spectrum. Um, and then we are realizing that this in the denominator here is just my group G flux. And then with that diffusion coefficient, what we're doing is we're rewriting it using the definition that the diffusion coefficient is the same thing as 1 over 3 sigma transport. And so, yeah, that's just kind of two different ways that you might approach the averaging of that diffusion coefficient. But either way, what we're going to end up working with is this D sub G, which is that group average diffusion coefficient. And if we put all of those things together, then we will have our multi-group diffusion model. So just kind of going back term by term with the results that we found, for the net leakage term, we had the negative gradient of that group, of the diffusion coefficient for group G times the sorry, this was the divergence times the gradient of my group G scalar flux. That was what my net leakage term looked like. Then we have a plus sign and we have that total interaction term. So that's going to be sigma T for group G, which could vary with position, times the scalar flux in group G. And then that was equal to, and then on the right side, I had my scattering term and I had my production term. And so the scattering term, and both of those had those big sums. So we had a big sum going over all H's. And then I had, for my scattering term, I had a sigma S to go from group H into group G. That could depend on position. And when we have scattering reactions, it's always the initial neutrons that are participating in the scattering. So the flux that's corresponding here is always going to be the group H flux, because it's saying, and that depends on position. Because that's basically saying I'm scattering from the group H into the group G. It's the group H neutrons that are participating in the scattering. So we use a group H flux for that product. And then I'm running out of room, so I'm just going to do a plus sign here for the rest of the right side. And then I had my fission term. And so I had like that chi G over K. And then I had a summation going from H equals 1 to big G. And then I had my group average nu F sigma F, which could vary with position. And that was for group H. And that was also multiplied by the flux of neutrons in group H. So this right here, we took that crazy complicated energy dependent diffusion equation, we integrated it over the group width, and then we used clever definitions of an average to convert that energy dependent equation into a multi-group equation where this gets greatly simplified. And instead of having these complicated integrals and stuff, each of my cross sections and my material properties are basically just like weighted energy averaged quantities. Um, and so it's important to also recognize that I'm writing this as an eigenvalue problem. So that's why we have a k in the denominator here. Um, and this is a steady state problem too. Like there's no time dependence in this equation. Um, and depending on however many groups I have, I would write this equation for every single group. So like if I have a three group model, then I'm going to have this equation written three times where little g would be one, then little g for one equation, little g would be two for the next equation, and little g would be three for the third equation. And if I had 100 groups, then I would have 100 of these equations where little g would go, I would have 100 equations where little g would range from one to whatever that big G is. And so, yeah, left-hand side, this is my net leakage rate for group G neutrons per unit volume, per unit time. This is my total interaction rate density for group G neutrons. This is the scattering, basically the in-scattering rate density. So it's the number of neutrons per unit volume per unit time that are scattering from group H into group G. And then this is my fission production rate density for group G, where I'm looking at the total fission production rate density, and then I'm multiplying that by chi sub G to say this is the total number of neutrons per unit volume per unit time born by fission, and then multiplying by chi G gives me the fraction of that total that just goes into group little g. Um, so these equations are a lot nicer. They're at least they're more simplified, and we actually have a hope of solving these equations, but there's still some complexity here, especially these sums. We might be intimidated by these sums. So what I wanted to do is kind of unpack the equations a little bit so that we can better understand like what those terms would look like if we expanded the sums. And that'll give us more appreciation for what we would end up having to do when we decided to like try to solve these equations. So what I'm going to do is I'm going to just assume a three group model. So that means that little g could be one, two, or three. And that means that I'm in total, I have big G equals three numbers of groups. So this was our equation. This is just rewriting that multi-group diffusion equation. And then what I'm going to do is I'm just going to write the equation for group one. So that means when I write the equation for group one, little g is equal to one every single time that we see a little g in the equations. So like on the left side, these g's, they all become one. And so that's what I have on the left side. And what I have on the right side, I'm gonna have to expand these sums. Um, oh, and I guess technically I've indexed these sums such that it goes up to the total number of groups that I have. So that's really the only change that I made when I went from the last slide to this slide, is that I'm saying big G is three. I just have three groups. So if I were to expand this in-scattering sum, how many terms am I going to get when I expand that sum? So if I had a sum that went from I equals 1 to 3 of um, let's just say x to the I. Yeah, perfect. Yeah, I'm going to have three terms because my index goes up to 3. And when I go through these various terms, right, the index is the thing that changes. So like if I were to write the first term, it would correspond to h equals 1, and g is 1 because we're looking at group 1. So the first term would be sigma s to go from 1 to 1. And then again, h is 1, so I'd be multiplying by phi 1. And both of these could vary with position. Right? That would be my first term when I let h be 1. And then I go up 1 on the index of h. So the next little h would be 2. So my next term would be sigma s to go from 2 to 1 could depend on position. And the flux is also based on the flux that's causing these scatterings, which is the group H flux. So in this case, H again would be 2. And then I would have a third term where little h is 3. So this would look like sigma s to go from 3 to 1 can be a function of position times the group 3 neutrons. So that's what these terms look like for the scattering term. Every time I change h is the only thing that changes in these sums. G is 1. Yeah, G is 1 every single time. So this is the scattering from group 1 into group 1. This is the scattering from group 2 into group 1. This is the scattering from group 3 into group 1. And I would have 3 terms for this fission production guy as well. And in this term, I only have h's inside of the sum, and this chi g is going to be the same. If I'm writing this equation for group 1, then for each of these terms, that chi g is just going to be chi 1. So I'm going to have like chi 1 over k times the terms inside of that sum. And so when h is 1, then I'm going to have nu f sigma f as a function of r for group 1 times the flux of neutrons in group 1. And then I'm going to have plus that nu f sigma f, which could depend on r for group 2 times the flux of neutrons in group 2, which could depend on r. And then I'm going to have that nu f sigma f can depend on r for group 3 times the flux of neutrons for group 3. That can also depend on r. So each of those sums, if it's a 3-group model, each of those sums will have 3 terms. So that right there would be like how I could expand those sums for like a 3-group model. And I've only written the equation for group 1. I would have another equation for group G equals little g equals 2, and I would have a third equation for group little g equals 3. And so if I kind of rewrite, if I look at this equation and I recognize that basically what it looks like on every term is that every term has some quantity being multiplied by either phi1 or phi2 or phi3. So what I'm doing here is I'm just moving these scattering terms over to the left side, and then I'm grouping all of the terms that are multiplied by phi1 together. So like this sigma s from 1 to 1 has a phi1 attached to it. So if I move it to the left-hand side, it picks up a negative, and then I've just factored out phi1 from all of those quantities. So this is like all of the constants that are multiplied by phi1. I would move the sigma s 2 to 1 times phi2 to the left side, which is why it has a minus sign here. And that's my only term multiplied by phi2 in terms of like the scattering terms. And I would also move the sigma s from 3 to 1 on the left side, so it also has a negative sign, and that's my only term multiplying phi3 on the left side. And then I keep all of these production terms on the right side, kind of as they were. The only thing I've done is I've distributed the chi into those terms. And so the reason I've written it like this is for 2 reasons. One, now I have all of my loss mechanisms on the left side, and I have all of my gain mechanisms on my right side. So in terms of and also the reason I've written it like this is because that phi1, phi2, and phi3, it is kind of looking like this is a matrix equation, and that I've got like constants times the fluxes that I'm trying to solve for. And so this is basically a eigenvalue operator problem in matrix form. If I think about L being my loss matrix and P being my production matrix, and then phi G with the arrow on top is my column vector of solutions. Um, so that is really helpful in the sense that in general, matrices might be scary, but they also allow us to solve, like, especially linear equations with constant coefficients. It makes it possible to solve them. And so I want to help us better see what this would look like as a matrix. But to do that, we would need the other equations for all of the other groups. So what I'm going to do when I jump to the next slide is just like kind of recognize that this is the form of this eigenvalue problem in matrix form. And then I want us to recognize that what I have here in the green, that basically is the equation that we just developed. So this would be my equation for G equals 1. What I have in this row effectively is my G equals 1 loss terms. And then this is my G equals 1 gain terms. And because of the matrix notation, this quantity in this first entry would be multiplied by phi1, and that was the first term that we had. And then this sigma s from 2 to 1 would be multiplied by phi2, and that was the second term that we had. And then the sigma s going from 3 to 1 was multiplied by phi3, and that's the third term that we had in that previous equation. And kind of similar story with these terms in my production matrix, that each of this first term was multiplied by phi1, the second term was multiplied by phi2, and that third term was multiplied by phi3. So we had a three-group model, which meant that we only had three fluxes, and that meant that this matrix like only really had three entries, but this could go down for as many groups as we had. And so like if I had a five-group model, then these matrices would be 5 units down and 5 units across. It would be a 5 by 5. Each of these loss and gain matrices would be 5 by 5s if I had a five-group model. And so the second equation would be like my G equals 2 equation. This third line would be my G equals 3 equation. And similar thing here, that would be my G equals 2 row, my G equals 3 row. If you were to rewrite that previous multi-group diffusion equation for those other groups, then you would end up seeing that's what those equations look like. And I've just written it here in a matrix form. Um, and Yeah, and so we can talk a little bit more about what we see in these matrices, and then we can also talk about how we might simplify these matrices for various assumptions about our problems. Um, so I guess the first thing I wanted us to do is just take a closer look at the scattering sums that we had. So like when we made it a three-group model, that in scattering rate density term had three terms. It was broken up into three pieces. And each of these pieces kind of represents like a different kind of scattering, depending on what group I start with and what group I'm keeping track of and what groups are participating in the scattering contributions either into or out of that group. So like it's probably helpful to draw just like a little picture where this is my number line. This is like my energy axis, and this would be group 1, this would be group 2, and this would be group 3. And so what we just wrote was the equation for group 1, which means that we're keeping track of just the neutrons that belong into this group 1. And for neutrons that are in this group 1, there's a couple ways that the scattering can occur. This first term says I'm scattering from group 1 into group 1. So it's like the neutron starts in group 1 and it has some kind of scattering reaction that just kicks it back into the same group. Like maybe it's a collision where the neutron doesn't lose that much energy or any energy. So the neutron has a scattering event, but it doesn't leave the group that it was currently in. If you stay in the same group that you started with, we call that kind of scattering within group scattering. So that first term represents within group scattering because I'm starting and ending in the same group. And then look at these next two terms. These next two terms say I'm scattering from group 2 into group 1. And the third term says I'm scattering from group 3 into group 1. So like if I think about this little picture, I'm either starting in group 2 and ending up in group 1, or I'm starting in group 3 and I'm ending up in group 1. So both of those I'm at, and remember, this is the way that my energy axis goes. And so these 3 and 2 are like lower energy groups. And if I'm going from 2 to 1, or if I'm going from 3 to 1, I'm scattering from a lower energy into a higher energy. So if I go from a lower energy group to a higher energy group, we call that upscattering. So both of these terms represent upscatter. I'm scattering up from a lower energy group into this higher energy group. So notice it's a 3-group model where group 1 is like my fastest group. And this right-hand bound right here, that's like my maximum cutoff energy. Like maybe that's 10 MeV or something like that. And so if group 1 is my highest energy group, there's no other higher group of neutrons that could scatter down into that group because it's the fastest group. So that's why there's no terms that look like downscattering for the highest group, because you can't downscatter into that group if that group is the highest energy group. So yeah, that's what we're saying here, that if group 1 is the fastest group, you can't have downscattering into that group. So what if we looked at group 2? If we were to write this scattering sum for group little g equals 2, notice now we're saying little g equals 2. So everywhere you see little g, it's going to be 2. And it might be helpful for us to just redraw our picture real quick. And I've got a 1, I've got a 2, and I've got a 3. So, and here it's group 2 that we're keeping track of. So we're kind of keeping track of just the neutrons that are in that group 2. So the first quantity that I have here is scattering from group 1 into group 2, right? So if I'm scattering from group 1 into group 2, for group 2, is this a downscattering quantity or an upscattering quantity? Perfect. Yeah, it's downscattering because I'm going into a lower group, lower energy group. So yeah, perfect. That first term would be my downscattering. It's my downscattering term. The second one is going from group 2 into group 2. So what kind of scattering is that? Starting at 2, ending back at 2. That'd be within group scattering, right? So that's within group scattering. And then lastly, what if I'm going from group 3 into group 2? What kind of scattering is that? That would be my upscattering, right? Because I'm going from a lower energy group into a higher energy group. So in that case, this represents my upscattering. Perfect. So for group 2, because it is like in the middle, it could have neutrons that scatter down into it or up into it. It has an upscattering term, it has a downscattering term, and it has a within group scattering term. And so it's very helpful for us to be able to like think about, even if it's just like drawing a simple sketch of those different groups, to be able to figure out based on the indexes that I see on those terms, which terms correspond to an up or a down or a within group scatter. So yeah, group 1 had no down scattering. Group 2 had all 3 types of scattering. And if I looked at group 3, we would see that group 3 only has down scattering or within group scattering. Because if I draw my picture again, if I've got 1, 2, and 3, and then if I'm keeping track of 3, if this is the group that I'm looking at, then the things that could happen is I could go from 1 into 3, which would be down scattering. I could go from 2 into 3, which would also be downscattering, or I could go from group 3 back into group 3, which would be within group scattering. So for group 3, there's no upscattering because group 3 is the slowest group. Oops. So like this energy cutoff right here would be 0. That's 0 EV right there. There's no lower energy than 0. So there's no neutrons with lower energies than the neutrons within group 3. So therefore, there's no way that neutrons from could upscatter into group 3 because it's the slowest group. So hopefully that like intuitively makes sense, but also hopefully that picture kind of just helps illustrate what we're talking about there. And so, yeah, if we wanted to write this equation more generally, that's what this is showing. If I had just big G numbers of groups and I didn't want to um, specify like a number, this is how I could write those scattering terms. And so yeah, just like hopefully we recognize that if I go from G to G, that would be my within group scattering term. So that's within group. The second term says I'm starting from indices that are going from 1 to 1 less than the group of interest. So if I'm going, that means that all of these indices are at lower indexes than the group of interest. And so if I'm going from a lower index into a higher index, um, that means that I am talking about downscattering. So this represents downscattering. And then similarly, for this third term, all of these H indices are higher than the index of interest. So these are neutrons that have groups higher than G going into G. And if my group is higher going into a lower group, that means I'm upscattering from those higher groups into the lower group. So this last one would be my upscattering term. So like if you had remember seeing this kind of term before with the different describing this is downscattering, this is upscattering, hopefully now thinking about it from like a 3-group model makes it easier to understand why we give them those kinds of definitions. And so if we think back to that matrix that we were just looking at, the L matrix, in that L matrix, some of the entries corresponded to upscattering, some of the entries corresponded to downscattering, and some of them corresponded to within group scattering. So that's kind of what I wanted us to take a look at next. That in linear algebra, if you have a square matrix, you can talk about the main diagonal, and then you can talk about everything above and below that main diagonal. So in this case, the main diagonal, that would be all of these terms. That's what we mean when we say the main diagonal. And then above the main diagonal, we have all of these terms that go from a higher index into a lower index. So all of the terms above the main diagonal represent upscattering. And then all of the terms below the main diagonal go from a lower index into a higher index. So those all correspond to downscattering terms. And then if I look at in the main diagonal, every term in the main diagonal contains something that looks like sigma t for that group minus the within group scattering for that group, right? Like here's the total for group 1 minus the within group scattering for group 1. Here's the total for group 2 minus the in group scattering for group 2, and so on. So that the main diagonal is what contains my within group scattering components. And by definition, since we always see the total minus the within group terms together, it's common because of that grouping, we give that quantity its own name. And that sigma total for a group minus the within group scattering for the group, we give that a name and we call that the removal cross section. So we can say sigma r for some group G is defined as the total cross section for that group minus that is a horrible sigma, minus the scattering that goes from that group to that group. So the total group cross-section minus the within groups cross-section, by definition, is the removal cross-section. And so that removal cross-section, it's the total interactions minus the within group interactions. The within group interactions don't knock the neutron into a different group. So what this effectively represents is the total number of interactions that result in my neutrons leaving that group, being removed from that group in some kind of collision. So that's the definition of the removal cross-section. And so because our original equation had that difference in the, if I just go up real quick, this original, or oh yeah, so whenever we wrote out all of our terms, right, we had that kind of grouping here, total minus within group, and you would have had that for every other group that you would have written equations for. So we can just rewrite our equations such that we're basically taking that big scattering, the scattering sum, and we're using, so this kind of is a helpful definition because we're making use of this definition right here. This was the quantity that we originally had in the multi-group diffusion equation, and we can, instead of writing one big sum, we can break it up into these three terms where each of them corresponds to a different kind of scattering. We could plug that into the multi-group diffusion equation. We could move the within group term to the other side, and then we can use the definition of the removal cross-section to rewrite our multi-group diffusion equation like this. So that's kind of what I've done to get to this equation right here. I rewrote that big scattering term into the three types of scattering. I moved the within group scattering to the left side, and then I grouped the total minus the within group scattering together and called that the removal cross section. So now along the main diagonal, I end up with that removal cross section instead of the total minus the within group scattering cross section. So that is now what that G by that L matrix would look like. And um, from there, I guess just wanted to mention a couple simplifying assumptions that we could have for these kinds of problems. If we neglect upscattering, then that the term that had going from higher indexes to lower indexes is dropped out of the equation. If there's no upscattering, then this term right here goes away. If there's no upscattering, that's all we're saying, is that if there's no upscattering, that term goes away, and that was how we got here. Um, and if there's no upscattering, then everything above the main diagonal just becomes a zero. And so now this would be considered a lower lower triangular matrix, because everything above the main diagonal is all zeros. Um, so if we think about another simplifying assumption, that so this can be made generally, like for any kind of numbers of groups, you could neglect upscattering possibly. In the two group model, we can also make an assumption about which neutrons are born in the fast group and which neutrons are born in the thermal group. If you think back to our fission spectrum, if we consider just a fast group and a thermal group, which which group are most neutrons born into? Are most neutrons born fast, or are most neutrons born thermal? Perfect. So most neutrons are born in the fast group, and therefore, if our total, if we have a chi1 plus a chi2 to give us 1, if we can make the argument that most neutrons are born fast, then we can assume that chi1, what that would mean is that chi1 is equal to 1, and chi2 would be 0. That's another assumption that you might see if you're doing like a two-group model. You might be told to assume that all of the neutrons are born fast, in which case your chi2 would be zero, and then in your equation for group two, you would have no fission production terms. You would only have fission production terms in the first group and the fast group because and which is a decent argument to make because of the fission spectrum, most neutrons are born fast, and then they have scattering reactions that kick them down into thermal energies. Um, so yeah, that is like everything that I wanted to say about multigroup diffusion theory, and that should put us in a good place to be able to work through and understand the rest of the problems that were on problem set three. And these would be like the main derivations to focus on from the this multi-group diffusion content. Um, Understanding just like how our group constants are defined in a two-group model. And it's kind of a cool thing that with this multi-group diffusion equation, you can now use this framework to rederive the two-group model. Like if you let big G be two, then you just have two equations. And the way that that would simplify, it would look just like your two-group model that we developed last time, except all of your quantities are group average. And you could do the same thing with a one group model. You could just take this equation and assume one group, and that's going to get you right back to one group diffusion theory, where every single cross section or material property is just a group averaged cross section over, if it's one group, then it's averaged over the entire energy range. So this kind of all feeds together. It's mostly two group model derivations that I was asking about on the homework. So derive and there's a derivation for getting a two group approximation for K effective, and there's also a two group a two group model where we can get a ratio of the fast to thermal flux components. And so this was all given in homework three. Well, I say homework in problem set three. Um, Also, in that question, I let you know what pages in Dr. Svedkov's notes where you can find the derivation. So if you had like looked at that before and it was confusing, now that we've kind of talked more, now that we've developed the multi-group diffusion equation, now that we've practiced breaking up those complicated terms so that we can see what the expanded form of that equation looks like, hopefully doing those derivations will make more sense. And that'll be the last stuff that would show up on exam three. So anything past there is not like if you're looking in Dr. Svedkov's notes, that's where we would be stopping. So that means that the review that I posted is accurate, and that yeah, this was where that review should have stopped as well. Um, I wanted to make sure I mentioned that we're not doing any numerical diffusion stuff. I think in either chapter three or chapter four, there's discussion of like numerically solving the diffusion equation. We haven't covered that. There's going to be no numerical diffusion stuff. So don't worry about that. And yeah. Um, when we come back after the exam, we still haven't finished chapter four. So there's some more chapter four stuff that I wanted to talk about. And we're just going to pick up on that when we get back. So we'll have our exam on Monday, and then this is where we'll pick up on a week from now on next Wednesday. Um, and so yeah, that's everything that we're going to see on exam one. Um, I finished a little early, so if we had any questions about anything on the problem sets, if we had any questions about exam questions, oh, I can go ahead and pass back our quizzes so that you can have those to study.